In this talk, I'm going to discuss ventilation-perfusion inequalities, sometimes called mismatch or heterogeneity. V with a dot on top of it stands for ventilation. A Q with a dot on top of it stands for perfusion, or blood flow. There are a couple of possible sources of uneven ventilation. I've listed just three here. One is a partial block in one of the bronchioles, allowing air to flow normally into one of the alveoli, but only a small amount of flow to the other. A second one could be an increase in dead space, and I will cover dead space in another talk. Dead space is just simply wasted ventilation. Air enters the respiratory system but doesn't participate in gas exchange. A third type could be a complete blockage of one of the passageways to an alveolus, but because alveoli have pores connecting them, air could enter one of the alveoli and then travel into the second alveolus. In this example, this alveolus is going to be underventilated relative to this one. COPD produces dead space. The destruction of the alveoli in this example right here leads to a large cavity, and the surface area to volume ratio becomes smaller and smaller. This leads to air entering the alveolus that doesn't reach the surface where the capillaries are and then is exhaled without participating in gas exchange. In a normal lung, there is a distribution of ventilation and perfusion throughout the lung. In the upper region, we call that zone 1. This is the cranial region called the apex. In this region, we have very low ventilation, very low blood flow. Here we can see flow, ventilation. But we have a high ventilation-perfusion ratio, in this case 3.4, and that leads to a very high PO2, 132 millimeters of mercury. I'm using torr here. Torr is just an abbreviation of the Italian who developed the technique of measuring pressure in millimeters of mercury. His name was Torricelli. 132 torr is the same as 132 millimeters of mercury. So very high PaO2, alveolar PO2, and very low PCO2. So this region is being hyperventilated. If we go down to the base of the region, caudal region, down near the diaphragm, we see a much higher blood flow, higher ventilation, but a smaller ventilation-perfusion ratio. This leads to slight hypoxia in this region and a slight hypercapnia. So a little bit increase in CO2, a reduction in O2. In the central region, we are just leaving that blank. This actually is a gradient. It's not we have one region, two regions, three regions. We've just simply broken them up into three regions here. If we look at this graph, we're looking at rib number 6 all the way up to rib number 1. So this is cranial, this is caudal. We're looking at perfusion. Very high perfusion here decreases as we move up toward the apex, cranially, until we have a very low perfusion up at the top of the lung. We look at ventilation. We see that at the base of the lung, caudal region of the lung, we also have a high ventilation, and the ventilation decreases as we move toward the apex of the lung. But perfusion is higher than ventilation at the base, and ventilation is higher than perfusion at the apex. This curve represents the ventilation-perfusion ratio at any position along the lung. Very low ventilation-perfusion ratio at the base, very high ventilation-perfusion ratio at the apex. If we look now at a figure showing the PO2 in the alveoli and PCO2 in the alveoli, the uppercase A stands for alveolus, or alveoli. A lowercase a we'll use for arterial. If we start here, let's look at this point right here. This is inspired air, PO2 somewhere around 150 millimeters of mercury, PCO2 down near 0. If we come over here, we're looking at mixed venous blood, PO2 around 40, PCO2 about 46. Normal PO2 and PCO2 is about 100 and PCO2 about 40. So if we look at zone 1, this is the high VQ zone. We see very high PO2. Zone 3, we see low PO2. And zone 2 is somewhere near the average. This curve shows all the possible PO2s and PCO2s throughout the range of mixed venous blood to inspired air. One of the reasons for the change in perfusion might be simply gravity, might be decreased resistance in the base of the lung as opposed to the apex of the lung. In fact, it's probably several reasons. Ventilation, however, we can see here in the apex of the lung. The resting alveolus has a higher lung volume at the apex than it does at the base. This is at FRC. Now we inhale. This is tidal volume. There is a smaller increase in the size of the alveolus, in the volume of the alveolus, in the apex, than there is in the base. The base, we can see a bigger ventilation than in the apex. Here we're looking at ventilation zone 1, zone 2, and zone 3. And we can see that in this next little animation here. This alveolus is collapsing down to a much greater extent than this alveolus. And it's inflating to a greater extent than this alveolus. So ventilation is high at the base, ventilation is low at the apex. Now I'm going to move to the computer model, and we can test different combinations of ventilation and perfusion in a two-compartment model. This is a two-compartment model. Two alveoli for simplicity. The blue color here represents the right alveolus, and the green color represents the left alveolus. For simplicity, I am using only two alveoli. Very simple lung. We are now looking at an overall ventilation of 4 liters per minute and overall perfusion of 5 liters per minute. This produces a ventilation-perfusion ratio overall of 0.8. 2 of those 4 liters per minute are moving into the right alveolus, and 2 of those 4 liters per minute are moving into the left alveolus. 2.5 of those 5 liters per minute are moving into the right, and another 2.5 to the left. So 2.5 liters per minute perfusion in each alveolus. Therefore, 2 over 2.5, our VQ ratio is 0.8 in green, our VQ ratio is 0.8 in blue. We have homogeneity, no mismatching of the ventilation-perfusion ratio. We can see mixed alveolar PO2 is 96.3, mixed arterial PO2 is also 96.3. No alveolar arterial difference. Looking at these graphs, we can see the oxygen dissociation curve using O2 content and partial pressure of arterial oxygen. We see one point here at a PA arterial O2 of 100 and a content of around 20 volumes percent. We look down here, this is the graph I showed you earlier, the alveolar PO2 PCO2 diagram, and once again we're at about 100 here with PCO2 of about 40. Let us look now at what happens if one of the alveoli is hyperventilated while the other alveoli is hypoventilated. So I'm going to move this up to about 0.75. There we are at about 0.75 ventilation ratio. We have 3 liters per minute going to the right lung in blue, and only 1 liter per minute going to the left lung. So this alveolus here in green is hypoventilated, this alveolus is hyperventilated. So we have 2 zones. Both alveoli, however, are equally perfused. So let's think of this as a supply and demand issue. You will hear me using supply and demand over and over again. The supply to this alveolus is low, but demand has not changed. Therefore, we're going to be removing oxygen at a much higher rate from this alveolus than we are from this. In this alveolus, supply exceeds demand. Demand hasn't changed. Supply has increased. What we see now is mixed PO2 in the alveolar air of 101 and a mixed arterial PO2 of about 82.5. When we look at these diagrams, we can see here that we have high oxygen PO2 in the blue or right alveolus, lower in the green or left alveolus, and this is our mixed arterial PO2 here, about 82 or so. On this diagram, we can see the mixed value of alveolar air is around 100 to 101. There's our right lung with a high PO2, low PCO2. Here's our left lung with a low PO2. One of the responses to an alveolus which is hypoventilated is a reduced perfusion. We call this hypoxic vasoconstriction. Therefore, we should see, in this example, a decrease in perfusion. Now, if we were to perfectly match the perfusion, in this example here, we've perfectly matched perfusion and ventilation. In the green, supply and demand now are back to normal. Low supply, low demand, but supply and demand are normal. Over here, we've got an increased perfusion to match the increased supply. So we've got an increased supply and an increased demand. Therefore, supply and demand once again are balanced. And we see a VQ ratio in blue here in the right alveolus, 0.8, VQ ratio 0.8. All our numbers are back. We now have a PO2 in the alveolus at 96, and again 96 in the arterial. No arterial alveolar PO2 difference. This is rarely, if ever, achieved. Hypoxic vasoconstriction reduces the flow to the hypoventilated alveolus, but does not necessarily match. So we're probably going to be something, let me bring this down to about here, about 0.6. So what we can see now is that we've reduced the alveolar PO2 from about 101 to 98 and raised the arterial PO2 from about 82 to nearly 90 millimeters mercury. The alveolar arterial PO2 difference has decreased, but we're never going to get right back on normal. We could do the same trick with perfusion. In this example, the demand has increased in the right alveolus, the blue color, but supply has not changed. We still have 2 liters going to each alveolus, but we've increased demand, we've increased blood flow. Demand is now exceeding supply. We see our PO2 dropping in this alveolus, and over here we see the PO2 rising because demand has been reduced, but supply hasn't changed. In this alveolus, the supply is higher than demand. In this alveolus, supply is lower than demand. Now I'm going to add CO2 to the figures here. Now we're looking at PCO2 of 38 points, about 39, PCO2 of about 39. We have approximately 39 in the blood. And now let's increase ventilation to one of the alveoli. Once again, I have 3 liters per minute going to the right lung and only 1 liter per minute going to the left lung. We went from about 39 down to 36 on this right alveolus, and we went from 39 up to a little over 41 on this alveolus. There's very little difference in CO2 between these 2 alveoli. Therefore, arterial PCO2 hasn't really changed very much. It's 38.9, which is where it was before. So we have a low CO2 in this alveolus, which is hyperventilated. A high CO2 in this alveolus is hypoventilated. But when they mix, we come right back to normal. The reason why CO2 does not behave like oxygen is that CO2 doesn't have an equivalent oxygen dissociation curve, or CO2 dissociation curve. So we really are looking at an arithmetic mean. In this case, hyperventilation, low CO2, hypoventilation, high CO2. But we end up back at the normal with the arithmetic mean being 38.9. Well, that concludes my discussion on ventilation perfusion, mismatching, heterogeneity, or inequalities.